Have you ever just stopped and wondered how a machine, right, a chunk of silicon and code, can write a poem, or answer some super complex question, or even code something new? I mean, it really does feel like magic, but it's not. It's actually this fascinating journey that starts with simple counting and ends up building something that looks a whole lot like an artificial brain. Okay, let's dive in and really unpack the science behind all this generative AI we're seeing today.
It really all kicks off with this simple, almost deceptive question. I mean, think about it for a second. How does a computer know which words are supposed to follow each other to create not just, a sentence that makes sense, but something with rhythm, rhyme, and maybe even a little bit of emotion? Well, to get to the bottom of that, you have to understand that at its absolute core, modern AI is a prediction engine.
And here's the basic recipe. First, you start by feeding the machine a gigantic library of pretty much everything humans have written. Think a huge chunk of the internet. Then, you train it on one single solitary task. Just predict the next word. You do this over and over, literally billions of times. And finally, you fine-tune it a bit so it's helpful and knows how to follow instructions. For this explainer, we're going to really dig into that crucial second step. So, let's start at the very beginning, with the first real attempt to solve this puzzle. The source material calls them small language models. A simple, but hey, a pretty powerful first step.
This first idea is called an n-gram model. And for a second, just forget about understanding meaning or context. An n-gram model is basically just playing a game of statistics. It looks at the last couple of words in a sentence, like the cat sat on the, and then it just asks, okay, based on every book I have ever read, what word most commonly comes next? That's it. It's just count.
All right, let's use this famous line from Shakespeare as an example. Let's say our model has read all of Shakespeare's works and it comes across the phrase, buds of May. So what word is it going to predict comes next?
Okay, now what's so interesting here is just how simple this is. Using a 3-gram model, it just looks at the 2 words of May, finds every single time they appear in its data, and then it just counts what follows. Turns out the word and showed up most often, so boom, it gets the highest probability. And what do you know? The actual next word in the sonnet, and, is right there at the top. It's simple and it kind of works, but only to a point.
So you'd think the next logical step is obvious, right? To make it better, we just give it more context. So instead of looking at the last 2 words, what if we look at the last 9? If we crank it all the way up to 10, do you think the model gets smarter, or does it actually get worse?
Surprise! It gets worse. A lot worse. And this just perfectly shows the model's fatal flaw. By demanding an exact match for a really long string of words, the chances of it finding that exact same sequence in its training data drop to basically 0. The n-gram model is just too rigid. It doesn't have a sense of close enough. It really needs a way to understand what words mean, not just what order they come in.
So to get past that roadblock, we have to make a huge leap. We've got to go from just counting words to actually understanding what they represent. We need to map out the entire universe of words.
Just think about this sentence. I should turn right at the light, right? The word right is in there twice, but it means 2 totally different things. One is a direction, the other is, well, it's asking for confirmation. An n-gram model would be completely lost here. It just can't get that the same exact letters can have different meanings depending on what's around them. That's the problem of context.
And the solution is this amazing concept called word embedding. This is a game changer. Instead of treating words like unique strings of text, we start to represent them as coordinates on a map. A huge, multi-dimensional map of meaning, where words that have similar meanings are placed close to each other.
Just look at this. It's like a 2D slice of that map. You can see fruits like apple and pear all hanging out together, way over on the other side of the map from animals like dog and cat. But here's the part that's truly mind-blowing. The distance and the direction between words actually captures their relationships. You can literally do math with words. If you take the coordinates for king, subtract the coordinates for man, and then add the coordinates for woman, the point you land on is incredibly close to queen. It's wild. This gives the AI a conceptual grasp of language, a real feel for how words relate to each other, even if it's never seen them in that exact context before.
Okay, so now we have a way to represent the meaning of words. But we need an engine that's powerful enough to actually process all these new complex relationships. We need to build an artificial brain. And the inspiration for this comes straight from biology. So on the left, you see a biological neuron. It takes in signals and sends an output signal out. And on the right, that's its mathematical cousin, the artificial neuron. It takes numbers in,
does a very simple calculation, and passes a new number out.
So then, when you connect thousands or even millions of these artificial neurons together in layers, you get what's called an artificial neural network, and it's a system that's designed to do one thing incredibly well: find patterns in data. The coordinates for a word go in one end, and a prediction for the next word's coordinates comes out the other.
Now, I know this can feel a little abstract, so let's walk through a super simple visual example to see exactly how these networks think. We're going to use a really complicated tool to solve a simple problem just so we can see the mechanics in action.
Imagine we want to teach a network to recognize if a line in this tiny little 2x2 grid is horizontal or vertical. So here we've got a horizontal line. First, we convert the image into numbers. Let's just say red pixels are -1 and white pixels are 1. And we feed them right into the input layer of our network.
Those numbers then travel along these connections to the next layer, and each connection has a weight, which can make the signal stronger or weaker. You can think of these weights as millions of tiny little knobs that the network can tune to get the right answer. And each node in this next layer, it just adds up all the signals it gets. It's just a cascade of really, really simple math.
As the signals keep flowing through the layers, the calculations just continue until they finally reach the output layer. And here, the node with the highest score wins. In this case, after all that math, the horizontal line node is the one that lights up. The network correctly identified the pattern.
So here's the most important part. No single node in there is smart. The intelligence is emergent. It's not that any single part of the network is thinking. The thinking is the network. The whole thing learns by making tiny adjustments to the weights on all those connections, turning all those little knobs again and again until its final output gets more and more accurate.
Okay, so let's bring this back to something a little more intuitive. Let's say we're training a network to tell the difference between cats and dogs. After training on thousands and thousands of images, the network might actually learn to create its own internal animal space, where all the cat-like features cluster together in one area, and all the dog-like features cluster in another.
And if we could somehow peek inside the network while it's working, what we'd see is just fascinating. The first layers might learn to recognize really simple things, like edges or colors. Then the next layers would combine those to find textures, like fur. And deeper layers still would combine those to identify complex features, a silhouette, pointy ears, whiskers. The network literally learns a hierarchy of concepts, all on its own.
So let's just quickly recap the journey we took here. We started with those simple n-gram models that just count words, but they ultimately fail because they have no context. Then, the big breakthrough came with word embeddings, which gave the AI a true map of meaning. And finally, deep neural networks gave us the engine, a powerful pattern-finding machine that uses those maps to make incredibly nuanced predictions about what words should come next.
And all of this brings us to one final, kind of profound question. We've seen that something that looks a lot like understanding, maybe even creativity, can emerge from a ridiculously simple goal. Just predict the next word. When you scale it up with massive amounts of data and a brain-inspired architecture. So, if a machine can learn the patterns of language this well, what does that really tell us about the patterns that make up our own language, our own thought, and our own intelligence?